So here is the awaited lecture on line integrals. So first, what you should remember is that integrals in Calc 1 were just done in a plane. So you had a straight axis, and on this axis you had a curve. Let's say the curve was z equal to y squared, and then you integrated from a to b. And remember, what is it that you did when you integrated? Integral, the sign s is it's merely a sum. This symbol stands for sum. So what you do, in essence, you sum a lot of areas of very thin rectangles, and the altitude of each rectangle, let's say a rectangle at some arbitrary position y, will have in this case altitude y squared, and dy is the width of the integral. So you can see this means just sum up all the areas of very thin rectangles from the point A to the point B, and then you obtain the area. Now you can imagine that that the picture, this two-dimensional picture, is drawn on a flat piece of paper outlined by those dashed lines. Now the integral certainly will not change if I were to take this paper and I would rotate it to some axis which I call the v-axis, right? If I just took this and rotated it around z somewhere, then I still have the same picture. I still have the same rectangle, so I still sum up the thin areas of the rectangles that I can stack underneath the curve z equals to v squared. I just relabeled it. I changed the letters from y to v, but that's just a cosmetic change. The meaning remains the same. Now, if you keep this analogy of a piece of paper, you might ask, what would happen if I were to take this piece of paper and I were to twist it? So this is a contorted piece of paper lying over the contorted v-axis. Still, clearly, if I were a two-dimensional creature living in the vz plane, clearly, even though it now curves, the surface still is very much a two-dimensional space, very much a plane. If I were living in this space, I could have just been walking along the v-axis. I might not have noticed that there is any curvature at all. And if you ask me to calculate the area under this curve, it still to me is just z equal to v squared. And still, I'm just adding up the areas of very thin rectangles that I can stack from a place starting at A on the v-axis and ending on B on the v-axis. It doesn't matter what you do to v within within the space. It seems that I'm just doing exactly the same procedure. That still is the area. However, you see, we are not quite clear on this axis how it's positioned, and we don't have necessarily a nice description of this curve, right? Because we are viewing it from the perspective of three-dimensional creatures living in the x, y, z plane. So we want this information translated to us in a language that we can understand. So again, right, I have to explain what is it that I'm doing. How am I adding areas of those rectangles using the x, y, and z axis? So the first step is possibly to try to describe this curve in terms of x and y. I could take the approach of, well, walking on it. And as I walk on it, I keep a timer. So that's where you have the t, I keep a timer. And at each moment of time, I notice where am I against the x-axis and where am I against the y-axis. So then I parameterize the v-axis as v of t equal to xt, yt. Okay, so then as I stop, let's say at this point x and the corresponding point y, I want to describe the width of the rectangle I'm seeing here, right? So I made it a bit thick. It's microscopically thin, but here is a rectangle. Here is the altitude. The altitude here is v squared, and the width is dv. What is the width? Well, the curve v, to make this procedure implementable, is called rectifiable. It has to be rectifiable. And what it means is that if I'm small enough, the curve will locally look like a straight line. So you see, I drew it in green. So locally, this looks like a straight edge lying in the xy plane. So how do I measure the length of that edge? Well, if this edge is of length dv, dv forms the hypotenuse of a right triangle, where the vertical side of the right triangle is dy and the horizontal side is dx. And so dv by Pythagoras theorem equals to the square root of dx squared plus dy squared. Right? Pretty much this is the formula that I will get. Now, how do I understand what is this in terms of my parameterization? Well, very simply, I can divide dx by dt and multiply by dt. Divide dy by dt and multiply by dt, which afterwards I can just simply factor out of the root sign. So you see, there would be a dt on the bottoms. Therefore, when I factor and then multiply it by dt squared, and this by dt squared, which I can factor outside of the root sign, and I obtain root of dx dt squared plus dy dt squared times dt, which ends up giving me the derivative, the x-coordinate derivative of the parameterization squared plus the y-coordinate derivative of the parameterization squared, which I take afterwards the square root of. Okay, so make sure you understand this idea. It's completely geometric. So we have, we measure simply this length, and we use Pythagorean theorem because this length is slanted. It's not quite parallel to the x-axis or to the y-axis. So we can draw this tiny triangle here and make the measurements. See, Leibniz notation for derivatives is rather useful here. So it's very suggestive, right? So we just divide by dt and multiply by dt, factor it out, and we have this formula which we right away recognize. Now, the second part, so we made the sense of how to describe the edges that form the path v. But now the next thing is, how do we understand this blue curve here? How do we understand z equal to v squared? So perhaps we can imagine that that there is a function of the variables x and y that intersects with this paper surface, with this, we can call it a plane if you want to, with this distorted paper plane. So there is a curve that will intersect, and that curve will be described as z equal to f of xy. Okay, so z equal to f of xy. What it means, in other words, is that if I walk along the parameterization, if I'm at xt, yt, which correspond to a point on the v-axis, then the altitude will be a point on the blue curve. So in other words, you see this coordinate, which involves three coordinates: the x coordinate, the y coordinate, and the z coordinate, really can be also described as the two coordinates v squared, the original curve. Yeah. So now we are pretty much ready to translate the integral from ab v squared dv to its form that's understandable from the perspective of the xyz coordinate system. So what we can observe is that there is going to be a time, call it time alpha, which corresponds to with which x of alpha, y of alpha will be the point A on the v-axis. There is also a time beta at which x beta, y beta is at the coordinate B. So now we have made the full parameterization. The integral from ab v squared dv now is translated to be the integral from alpha to beta of f xt yt, which is basically evaluating the function at the curve. And that corresponds to, in this example, it's like v squared, times the square root of the x-coordinate derivative squared for the parameterization plus y prime of t squared. So let's do a calculation just to be sure that we understand how that's supposed to be done in practice. Here. So let's try to evaluate this integral. So this is an integral over the curve C, where C is the upper half plane of the unit circle. So what we have is 2 plus x squared y squared. So this, I don't recognize this function over this curve as something necessarily that simple, but it's not necessary. So here is what we have here. We need to parameterize the upper part of the circle. So the easiest way to do that is to say that the parameterization is cosine t sine t, and that's my x, that's my y. Then I need to figure out what's the derivative of this parameterization. The derivative is minus sine t cosine t. And then, so this roughly will correspond to dx and dy. So then what I do is I square this number, I add the square of the second number, and I take the square root, and clearly I get 1. So the magnitude of c prime of t is 1, which means that dv, so to speak, right, is the same length as dt. Now, I then plug the cosine of t instead of x, and I plug sine t instead of y. So I get then the integral from 0 to pi. That's because it's a upper part of the circle. So from 0 to pi, 2 plus cosine squared times sine. Then when I simplify this, now it becomes an exercise from single variable calculus. I just simplify this, integrate, and I get 2 pi plus 2 divided by 3. So that's how the calculation will be carried. Now the integral has this line integral has a short notation, which we just write the integral over c of f times ds. Now what's this ds? This ds is in my picture over here. That's just the segment, right? The segment that's on the axis, on this v-axis, on this curve. Now you might wonder, why do they use the letter s? Why is it ds? What ds is supposed to signify? My hunch is that s here refers to the German word for a path, and path in German means Strecke, die Strecke. So that's a much better word than I think a line, because you can clearly see that. Well, here we're not really integrating over a line. Just this axis has been curved, has been twisted. So we are really integrating over a path. All right. So it might be interesting to note that the way we define the path integral is it seems that we are using one particular parameterization. So the idea is, this is the curved axis. You take a particular parameterization, like in the example we had, the curved axis was the upper part of the circle, and we parameterized by cosine t sine t. So if we we made a specific parameterization of the upper part of the circle. Is the integral going to be different if I pick another parameterization for the same circle? And the answer is the integral is completely indifferent to what particular parameterization you pick for the circle, as long as the parameterization is such that as you're walking, when you parameterize, you can imagine you do it with time, as that you're walking along the path in such a way that you are not coming back. You pass only once along the curve, never to return to a place that you already visited. So you might guess, of course, that again, however you describe, all of this is supposed to be a description of doing a very simple process, just adding up areas of rectangles, multiply the width by the height. And it doesn't seem to matter that if you describe this process one way or another, there should not be any difference. You should get the same exact numeric value, the same exact sum of areas. and that is indeed true, right? So so the path integral or the line integral, however you like to talk about it, is well defined. And here is a way to see it, right? So first of all, suppose that we have we have this curve that we want to walk on, and the curve is parameterized on one hand by v of s, where s varies from delta to lambda, and on the other hand, it's parameterized over here from alpha to beta by wt. So in other words, those are two different descriptions. Maybe two different people are walking along the same curve, and they are in different places on this curve at different times. But all of them, let's say, are walking in such a way that, let's say this person, v of s, is walking. He is not going to return to a place visited. So he's not going to go back. He's just walking onwards along the curve, like I'm showing with this red marker, right? Maybe the other guy is walking in the opposite direction. That doesn't matter. That's a different parameterization, as long as you are not going back on your path. You're not returning to a place that you already visited. So you can you see that we can see that all the parameterizations are essentially like WT. You can always modify a parameterization by just changing the speed, or by just altering the time here, right? By altering how you move at those points. And formally, this is how you do that. So what you have is I want to describe V in terms of this parameterization W. What do? Well, I see that at some S, I have V of S, it's mapped to this point, and then this point corresponds to some T. So what I do, I take the inverse image, because I mean, I see this point, it was visited only at a particular moment of time. So I take the inverse, and now I am at this T. So now what did I do? I defined the function T of S. I defined a function that describes for each S, what should be the corresponding T to be there. And so you can see that V of S equals to W composed with W inverse of V of S, which means it's W of T of S. Okay. And that is to say that that every parameterization can be just can be programmed, so to speak, by modifying the time. So in other words, imagine that you have one person, you recorded it on video. One person was walking along this curve, let's say starting at this point and moving towards this point. Starting at this point and moving towards this point. And yes, and you recorded it on YouTube, and then you have the time delta and the time lambda, right? So the YouTube video runs from this moment to this moment. Now you can modify the particular recording that you have to match the observations of anybody else that walked on this curve, whether from this point to that point, or starting at this point back to this position, right? Doesn't matter. I can always just I can just tweak the time. I can program the time to move in such a way that so that the time bar usually runs smoothly. Time bar runs smoothly. I can make it run here faster, here slower, here faster. I can adjust it, and that's what I mean by this T of S. It can be adjusted. So here, is basically if I have one parameterization C of T, any other parameterization then will be C of TS, where what this means is just adjusting the time. And you can see that the integral is invariant under change of parameterization, because if I change the parameterization, it will be this integral from delta to lambda f of CTS, dx ds, dy ds, and ds over here. Now I can place here dt. I just divide by dt and multiply by dt, and I have here dt over ds squared. Here as well, I have dt over ds squared, which after when I factor out from the root, I have the absolute value of dt ds. And now what is this integral? If you do a u substitution, this is just the integral for the original curve where I just used t. So it's just an obvious chain rule that happened here. So by u substitution, I can make it look like the line integral defined over t. So we might as well have a piecewise smooth curve. In other words, when we take derivatives, but not, we're assuming that the curve is smooth. But here is an example of a piecewise smooth curve. So C1, this piece is smooth until we get to this point. So this is a non-differentiable point. Then we continue with C2, then with C3, C4, C5, C6, and so on. So what's truly happening? We are, again, right, so we took a piece of paper, we folded it, it has a picture, we folded it along this line. So the piece of paper is actually coming at you. The z-axis is coming at you from here, this point. And we are, again, we are just doing single variable calculus here. We are adding the rectangles that are, whose fundaments are lying along those curves. And of course, it's pretty clear then that the integral is additive. I can take this integral over C1 plus over C2 over C3 and all the way to C6. And why is that? Simply because it just, you see, I can add first the rectangles that are stalked. They are thin rectangles, the areas that are stalked over C1. And then I can add the rectangles over C2, then over C3, etc. Right? I can add the areas sequentially. I can take them batch by batch. So here is an example. So we want to evaluate 2x ds over the curve C, where C consists of two pieces. The first piece will be a parabola from a parabola y equals x squared from the point 0, 0 to the point 1, 1, followed by the vertical line segment from 1, 1 to the 1, 2. So here is, so it's convenient to describe this curve separately from this curve. They have different formulas, it's convenient for integration. So the curve C1 can be simply described as the graph of this parabola, which is t squared, for t being between 0 and 1. And the second curve, C2, is a curve where I'm only moving vertically, so I don't bother the x coordinate, but the y coordinate is changing from 1 to 2. So then I need to calculate the magnitude of the vector C1 prime and the magnitude of the vector C2 prime. So C1 prime of t is the root of 1 plus 2t squared, which is root of 1 plus 4t squared. Okay, what is this measuring? Again, this measures this small segment on this, if you imagine the v-axis back in the picture above, right? Just this slanted segment. And that's locally what's the length of that segment. We would take the segment and multiply by the altitude, which is furnished by the function fxy equal to 2x. So we get this length. Then similarly, if we take the derivative for C2 and calculate its magnitude, this is 0, this is 1. We square each derivative and take the square root, and we get that C prime of t is equal to 1. So then the integral over C of 2x ds is the integral over the curve C1 plus the integral over the curve C2. So now I just need to describe it in terms of my parameterization. So here in the first case, t goes from 0 to 1. And what I have is x is equal to t. So it will be 2 times t times the factor c prime here, right, in absolute value. So it would be root of 1 plus 4t squared square root. Now for the second part for C2, what do I do here? I know that x for the second part equals to 1, and then the corrective factor is simply 1. So what we're doing is, of course, we have this plus integral from 1 to 2 of 2 times dt. And we calculate now. It's just simply a matter of calc 1. We use u substitution. You can see that 4t squared, its derivative essentially is like 2t. So just by a little simple manipulations, you just get this number. Right, so the result, once you end up calculating, is just 5 root 5 minus 1 over 6 plus 2. So you might, of course, if you study a little physics, well, you might think that what is a line integral good for? You might, even if you actually study it, think it's not really good for anything. But, we might interpret it as follows. So we have, let's say we have a wire, C, and the wire is it has different it's made of different materials, so it has different mass as you move along the wire. So let's say rho here is the density function. I imagine giving density to any point xy or any point in the vicinity that contains the curve C, and that's my linear density function. So density multiplied by length will give you the one-dimensional, the linear mass. So what we have is this is an integral from yes. So this full integral can be interpreted as equal to the full mass of the object, of the wire, and I can use this to calculate the center of mass of the wire. So for example, if you know how to calculate center of mass, you take the x-coordinate multiplied by the density function and the corresponding length. So x, the position x multiplied by the mass segment, similarly y multiplied by the mass segment, and then you add up over all the mass segments and divide by m, and that gives you the center of mass. Again, I'm not at this moment explaining physical concepts. If you know what center of mass is from physics and how to calculate it, you can recognize it here. So here is an example. A wire takes the shape of a semicircle x squared plus y squared equal to 1, and y is bigger than 0. It means that it's the upper part of the circle. And imagine that it's thicker near its base than it is near the top. So the density is proportional to the distance of a point. So at any point, the density is proportional to the distance of the point from y equals 1. So in particular, we want to calculate the center of mass of this wire. So here is how we proceed. So the density function is the distance between the given point xy and the point x1, right? And that distance is clearly 1 minus y, because we can assume, because we're dealing with a unit circle, we can assume that y is less than or equal to 1. And the k here is just a constant of proportionality. So what do we have here? We have that c of t is, I parameterize the wire. I parameterize it again as cosine t sine t, where t goes from 0 to pi. And I know that the magnitude, if I take the derivative and I measure the length of the derivative, it will be of unit length everywhere. Which means that the mass, which ends up being the calculation for integral from 0 to pi, rho cosine t sine t times the root of x prime squared y prime squared, which happens to be equal to 1, times dt. And well, what is that? I know that my density function is k times 1 minus y, so I factor out the k, and I have 1 minus what's y in our parameterization. Y is, this is y, right? So it's sine of t. And now this becomes a simple matter of integration, calc 1 stuff. So that is k times pi minus 2. Now I want to calculate the integral over the curve of x times the density function. So what is that? This is k times cosine of 1 minus sine of t. You might, of course, observe by the very property here, by this problem, the arc is symmetric, right? The arc is symmetric around, well, the arc is symmetric around the y-axis. So by symmetry, you would expect that x should be balanced exactly at 0. You could calculate, of course, this integral, but you right away can figure out that the answer is 0. It's a little bit more involved to calculate the same quantity for y, for the y part. So here again, we have the y coordinate multiplied by the density when I changed it. It's parameterization, so here it is. So when I calculate it, I end up with k times 4 minus pi. And so what I do so I have 0 for the first calculation, 4 minus pi to the second calculation, and all I have to do is divide each quantity by the mass. And the mass was k times pi minus 2. So the k's then cross out, and I have this point as my center of mass. So there is yet another type of line integral that we need to consider, and that is the integral basically, let's say what we're trying to do in physics is measure the work done by some vector field on a particle that's rigidly attached to a path. So imagine that this is like a roller coaster, and this is a cart, and this cart cannot move away from this roller coaster. It's fixed to it, and there is a force pulling it. So the force pulling at the bead, at the particle, has two components. It has the x component and it has the y component. And let's say we have a full description of what the force field does to any point xy. So at some point xy, it will be some function pxy at the x coordinate, qxy at the y coordinate. And we want to know what is this force, this force doing to this particle. So if you know the concept of work is, so this force, you see, much of it is wasted. Part of this force is trying to dislodge this wire, to dislodge this particle from the wire. So let's say it's this part, it's whatever is perpendicular to my path. This part of the force will be trying to push the particle down. And the other part of the force, I can decompose the force into a component along the purple line segment and a component along the green line segment. The green line segment force is just resisting the wire. It's too weak to do anything, and it's not affecting the motion of the particle. The component that runs parallel to the wire, you see, if the wire is very small, this segment, this is roughly supposed to be the segment microscopically zoomed in at the curve. So the work done here locally by the force F is the component of the force along this wire, which can be calculated as the magnitude of F times cosine of the angle between them. That would be this component, multiplied by the length dx dy, by the distance traveled. So force is distance, work is force times distance. Okay. And if you recognize, the quantity here is, okay, this is ds. So this squared plus this squared square root, that's ds. So ds times the force times cosine theta, it's the same thing as the dot product between the force F and dx dy. So because I decompose the force F into its components P and Q, that ends up being locally P times dx plus Q times dy. So this, now what happens over this curve is that I have many such line segments. This, of course, is grossly exaggerated to make it visible. dx will be tiny. So there will be many dx dys along this path. So you should imagine that this path is like a chain of tiny line segments. And over each line segment, I make this calculation of the dot product, which ends up being this. So I end up adding all those dot products until I get to this edge. And that means what I'm doing is I'm integrating along this curve the expression p dx q dy. So let's just see how that's supposed to work. So let's try to evaluate this integral, where c is the line segment first from -5 to -3. Sorry, -5, -3 to 0, 2. So we go from this point to that point, and it's just a line segment. And b is just this parabola arc. So let's begin with a. So first of all, what is our vector field? So you can see that the vector field is its components are y squared and x. So y squared and x, because you can see where you took the dot product. It's this expression times dx plus this expression times dy. So how do I parameterize this line segment? Well, one very simple way, look here in this red box, I want to start at this point and end at this point. So I take this point, multiply by 1 minus t. And I take the other point and I multiply by t. Look what it achieves. If I put t equal to 0, I get this point. If I put t equal to 1, I get this point. So in 1 second, from 0 to 1, I go from this point all the way to that point. In a way, that's you can see that's for any t, that's an average. So then I need to bring it together. So first of all, you can see what would be if I add it up. What would be the x coordinate? What's x here? X ends up being -5 times 1 minus t, and y ends up being simply -3 plus 5t. So now I can now parameterize the entire situation. So what is y? Y here is -3 plus 5t. So I take y as I am required. I square it. And what's dx? When I take the derivative, dx and dy are all equal to 5 dt. So dx equals to 5 dt and y equals to 5 dt. So that's what I get. I get dx is 5 dt, dy 5 dt, and then x equals to 5t minus 5. And then I go through the business of integrating it, and I obtain -5/6. Now, for the other path, I am asked to travel from this point to that point along the parabola. X equals to 4 minus y squared. So the easiest way to parameterize this parabola is to set y equal to t, and then x equal to 4 minus t squared. And that's what we do here. So c of t equals to 4 minus t squared t, where t goes from -3 to 2. The numbers I get from here, right? I need to go. I need to get from -3 to 2 on the y-axis. So here I have t between -3 and 2. All right, so then I have this curve. Now I take its derivative. So the derivative of that curve, the x derivative is -2t. The y derivative is 1. And this, I will take the dot product of this vector with y squared x, where y has to be replaced by what? So y is replaced here by t. So I have here, that's why I have t squared. So y is t, so t squared here, times -2t dt. And then this x is 4 minus t squared, and then derivative here is 1, so I just write dt. So then again, now I have this set up, factor out the dt. That becomes a very simple polynomial integration, at the end of which you get 40 plus 5/6 as your final answer. So a little over orientation. So you see, when you're walking from some point A to some point B, perhaps on Brighton Beach, right? So if you start at point A and walk to point B, implicitly you can just time yourself. As you're walking, you are creating a number line, right? Because let's say you're traveled, it took you 1 hour to travel, and let's say at the moment you started your stopwatch, now this is coordinate 0. Then let's say you walk, maybe you're running with constant speed, and then this is time equal to, let's say, half an hour, 1/2, and then this you end up at the point B 1 hour later. Right? After you began the trip, you were moving, and it took you 1 hour, and you are now here. So that's one. So now this curve, in a sense, now has been. Now it has made this curve like a number line, because you can see, I can imagine the notches. The notches are the notches of time. So 0 is this point, 1/2 is this point. So it looks like if I were to straighten it up, it would just be like a ruler, like a regular number line. Now, we also have an orientation, because we started at A and ended at B. So that's one orientation. The opposite orientation, if we call this orientation, if we say that this orientation is represented by C, the opposite orientation will then be represented by -C. It will be any path starting at B and ending in A, right? So again, when we consider paths in this discussion, we don't want to kind of, let's say, we don't want to go out, oh, I forgot something, and return. We don't want such paths. We are always moving forwards. So one sense, moving forwards here is from A all the way to B. And then there is another sense of moving another orientation where you start at B and you move all the way to A. Right? So they are opposite orientations. So if I decided that this is C, then this will be -C, because they point in the opposite directions. You can see the arrows point in opposite directions. So a very rough definition here is as follows. So suppose I have some parameterization. Again, I still call it by C. Strictly speaking, C is the geometric curve. And so there is the geometric pathway, and there is the path traveled. So the path traveled has more information. It has the information of the geometric shape that you traced, but also of the time where you moved for any to arrive at any particular location. Okay, so a curve. I imagine like empty Brighton Beach shore. And like the boardwalk. I imagine the empty boardwalk, that would be the curve. Now, the parameterized curve, I actually imagine to be the same boardwalk, but with notches, right? Maybe the notches are for time, right? So maybe where I was at 0 time, then at some other moment of time, then at some other moment of time. So I imagine like a number line. So I imagine this path is a marked curve. And of course, you can mark the same curve in so many different ways. So imagine that, just to make to abuse notation and not to make this distinction, imagine that I parameterize the curve C by the following path function from alpha to beta to R2, and that's just that's basically this curve, but with particular parameterization. -C will be any curve parameterized in the opposite sense. So the sense of A and B is reversed. A is my first location, and B is my last location for one parameterization. For -C, it's like the way back. B is the first location, and A is the second location. So one way to parameterize -C, you can see I can use the same parameterization and describe in terms of it -C. So -C of t will be alpha plus beta minus t, where t is still from alpha to beta. Why does it work? Well, think about it. If t equals to alpha, then we have alpha plus beta minus alpha. So I have C of beta, and I'm at point B. Yes, and then when t is equal to beta, I am at alpha, so that I arrived at point A. Right, so you can clearly see that this description here reverses the motion. It's like basically like rewinding a tape or like playing the video backwards. So you see, if you see a video where a person walks from point A to point B, then if you play the video backwards, this is just telling you to play it backwards, then you will see the other sense. You will see that the person starts at point B and walks backwards to point A. Now, it is pretty easy to see that if you have two paths that are moving in the same direction, they agree that A is first and B is second. If they're moving in the same direction, then the integral, the new line integral here, is not affected. But if you change the direction, as you can see here, right, the integral over this change direction will be affected. And here is why, right? So let's consider what happens if I integrate over the curve minus c, which means that when I parameterize, what do I do? When I parameterize, when I parameterize, I place into P this backwards curve, this minus c curve. That's parameterization. And then when I calculate dx, I get this number, and then I get an extra -1 because of chain rule, because I have here a minus t, right? So what's the derivative of dx dt? It will be like the previous derivative, with respect to just u times this is u, then it will be du dt will be then -1 dt, right? So I have this -1. I then take this -1, I factor it out, and I have an integral from alpha to beta of this expression. Now, if I make a u, so I can make a u substitution. I can borrow this -1, I can place it back. I make a u substitution where I take this to be u. So now I have a parameterization that resembles very much what I would get if I were to work with c, not with c minus, but with c. Except that, look at it, the integral begins at beta and ends at alpha. Now we can reverse the order of integration and multiply by -1. That's just a property from this integral is essentially a calc 1 integral, all right? So I reverse the order of integration and I place a -1 in front, and that is minus the integral over c. So you see, when I change the orientation, I introduce the minus here. And so you see, basically, if I take any other path that starts, let's say, at that point B and goes to the point C, you can verify that you will get exactly the same expression. So there is, in essence, when you do the calculation, depending on the orientation, you either get minus an integral of c or an integral of c, depending on, so that basically depends on just two types of parameterizations. So we can do the same thing in three-dimensional space. We can generalize the line integral to a three-dimensional space. It's just now ds, again, if you remember, s I think means Strecke. So ds will now be a line segment hovering in the xyz plane. So not in the xyz space, not necessarily in the plane. So clearly, I still do exactly the same thing. I mean, I have areas of rectangles where the altitude of the rectangle is described by this fxyz, and the width of the rectangle is described by ds. When I communicate what this ds is in terms of the xyz coordinate system, I get root of dx dt squared plus dy dt squared plus dz dt squared. That's just, again, the Pythagorean theorem extended to R3. So it's a very similar thing. We can extend the vector version of the line integral, right? So if I have a vector field with coordinates p, q, r, then and I have this space curve C, the integral over C of f ds will be simply the integral over C of the p dx plus q dx plus q dy plus r dz. Which, when I parameterize, what it amounts to be? It amounts to be integral from alpha to beta. I plug, instead of x, y, z, I plug c of t, and then here instead of dx, I have dx dt. I have dy dt instead of y here, and I have dz dt. So here is an example. So let's evaluate two more integrals and then maybe call it a day. So what is this? So we are integrating over the curve C, y sine z ds. So that's the first version of line integral here. So I need to I have a C. It's a helix given by cosine t sine t and t. So what I need to do is I need to measure the length of C prime. So I take the derivative. So derivative of cosine is minus sine, I square it. Derivative of sine is cosine, I square it. Derivative of t is 1. So I take the square root of this squared plus this squared plus 1. You can clearly see that sine squared plus cosine squared is 1. So we have square root of 2, which I can factor outside the integral sign. Now, instead of y, I put sine t. Instead of instead of z, so here instead of z, I put t. So I have sine t times sine t, which is just sine squared t. And this is, now it becomes a problem from Calc 2. How do you integrate sine squared dt from 0 to 2 pi? You can use the double angle formula. Here it is. And afterwards, I mean, you might notice that this part does not need to be integrated because now it is identically reduced to 0 once you integrate from 0 to 2 pi. And so we have really just the integral of 1/2 dt from 0 to 2 pi, which is 2 pi over 2 times root 2, which is root 2 pi. So here is another example that's now with the dot product version of the line integral. So we have a field y, z, x, and we want to integrate. We want to, in other words, to find the work done by the vector field on a particle traveling along the curve C, where C is built of two segments. The first segment is a line segment from this coordinate 2, 0, 0 to the coordinate 3, 4, 5. And afterwards, we follow by another line segment. This time it's a vertical line segment from 3, 4, 5 to 3, 4, 0. So we break this calculation into two parts. So we begin with parameterizing C1. Again, we begin at the point 2, 0, 0. So we write 2.00 multiplied by 1 minus t plus 3, 4, 5 times t. And yes, we can then bring it all together. Then I see that 2 plus t is my x, 4t is my y, and 5t is my z. Now you see I labeled, I take the derivative, c prime of t. It's 1, 4, and 5. I say this is dx, dy, dz, but what I truly mean is that this number times dt will be dx. So this number times dt will be dy. This number times dt will be dz. So what I have here? I have this dx. I replace it by 1 times dt. I have here dy. I replace it by 4 times dt. And finally, I have dz, which is 5 times dt. I put it over here. So I now took care of my dx, dy, and dz. And now I wonder what is y. Y is 4t. That's where I put it. What is z? Z is 5t, that's where I put it. And what is x? X is 2 plus t, that's where I put it. Now I then group it together, simplify, I have this integral, wonderful, and then this integral reduces to 24.5. Now over the second piece of the curve, let's call this C2 here. So there, the parameterization that I decided to pick, since I'm moving vertically, I'm only changing the z-axis. X and y are constants, so it's 3 and 4, and z is going from I chose it to be 5 minus t, because then if t is equal to 0, I'm at 5, and then when t is equal to 5, I'm at 0. So then t varies simply from 0 to 5. Now if I take the derivative, I have that dx is 0 times dt, dy is 0 times dt, because we're not changing along the x-axis. We're not moving along the x-axis or along the y-axis. And we're moving steadily 1 unit down along the z-axis. So dz equals to minus 1 times dt. So you can see that because dx is 0 and dy is 0, I end up only considering x times dz. Now x times dz, x is in this case 3, and dz is minus 1 dt. So I'm integrating simply minus 3 between 0 and 5. And it gives me minus 15. So thereupon, the calculation of over the full curve is the piece over C1 plus the piece over C2, which is 24.5 minus 15, and that yields 9.5. I hope this might have been a little helpful.